Most industrial plants begin with one essential requirement: a reliable connection to the electrical grid. This facility does not. Built in the vast open landscape of Inner Mongolia, the Chifeng Green Ammonia Project was designed around a different idea: generate the energy on site instead of importing it. That single decision changes the entire engineering approach. Instead of asking how to power a factory, the engineers asked how to build an industrial ecosystem that could operate independently. The answer begins with understanding the problem they were trying to solve. Global shipping moves around 90% of world trade, but it also depends heavily on fossil fuels. As international regulations push for lower emissions, the industry faces a difficult challenge: finding a fuel that can power large vessels over long distances while reducing carbon emissions. Green ammonia has emerged as one of the leading candidates because it can be produced using renewable electricity, stored as a liquid, and transported through existing industrial infrastructure. But producing green ammonia at this scale requires far more than a new fuel. It requires an entirely new energy system. Everything starts with renewable electricity. Wind and solar energy power electrolyzers that split purified water into hydrogen and oxygen. Hydrogen is then compressed and combined with nitrogen separated from the air. Inside the Haber Bosch process, these two gases react to produce ammonia, which is cooled, stored, and prepared for export. While the process appears straightforward, every stage depends on a continuous flow of energy. The challenge is not simply making ammonia, it is keeping every part of the system operating together. Unlike conventional industrial facilities, Chifeng was designed as a single integrated energy system. Renewable generation, electrical infrastructure, hydrogen production, ammonia synthesis, storage, and export are connected through one coordinated operation. Instead of functioning as isolated pieces of equipment, every system supports the next, allowing electricity generated in the surrounding landscape to become a globally traded chemical product. This systems approach is what makes the project fundamentally different from traditional ammonia plants. Projects like this depend as much on geography as they do on engineering. Inner Mongolia offers abundant wind resources, excellent solar potential, and vast areas of land suitable for utility-scale renewable development. Rather than transporting fuel to the factory is built where renewable energy is naturally available. That shift marks a new chapter in industrial design, where future manufacturing follows clean energy resources instead of fossil fuels. Now that we know why the project is here, it's time to see how that renewable energy is generated and managed. The journey begins with renewable power. Surrounding the industrial complex are large wind farms and solar arrays that generate the electricity needed to operate the entire facility. Unlike conventional power plants, renewable generation changes throughout the day as wind speeds and sunlight vary. That variability is one of the biggest engineering challenges facing large industrial facilities. Producing clean electricity is only the first step. The real challenge is delivering reliable power to a factory that must operate continuously. Instead of relying on a public transmission network, the Chifeng facility operates as its own integrated electrical system. Renewable generation, electrical equipment, and industrial processes are coordinated within a dedicated power network designed specifically for the plant. This allows electricity to be directed where it is needed while maintaining the stable operating conditions required for hydrogen production. In effect, the factory functions as both a power system and a manufacturing plant working together. Coordinating thousands of pieces of equipment requires far more than manual operation. A digital control system continuously monitors electrical generation, equipment performance, and process conditions across the site. Operators can respond quickly to changing renewable output while maintaining stable production throughout the plant. Rather than controlling individual machines, the system manages the entire facility as one coordinated operation, ensuring that renewable electricity is converted into industrial production as efficiently as possible. Every electron generated by the renewable power system follows a carefully engineered path. Electricity flows through substations, transformers, switchgear, and power electronics before reaching the electrolyzers. Each component protects, conditions, and distributes power so that critical equipment receives a stable electrical supply. Only after passing through this electrical infrastructure does renewable energy become ready for its next transformation, from electricity into hydrogen. This is where renewable electricity becomes a chemical feedstock. Industrial electrolyzers use electrical energy to split purified water into hydrogen and oxygen. The hydrogen becomes the foundation of ammonia production, storing renewable energy in molecular form for transportation and industrial use. But before electrolysis can begin, another hidden system must do its job first, preparing the ultra-pure water that makes this entire process possible. Every kilogram of hydrogen begins with water. Before entering the electrolyzers, raw water passes through multiple treatment stages that remove minerals and impurities. High-purity water is essential because contaminants can reduce efficiency and damage sensitive electrolysis equipment. Although rarely seen, this supporting system is one of the foundations of reliable hydrogen production. With purified water prepared, electrolysis begins. Electricity separates water molecules into hydrogen and oxygen without combustion. Renewable electrical energy is converted directly into chemical energy stored inside hydrogen molecules. This transformation is what allows renewable power to become a transportable industrial feedstock capable of supporting large-scale manufacturing and international trade. Fresh hydrogen must now be prepared for the next stage of production. Industrial compressors increase its pressure while purification systems ensure the gas meets the quality required for ammonia synthesis. Pressure, temperature, and flow are continuously monitored so that hydrogen can move safely and efficiently through the plant. Every molecule leaving this stage is ready for the chemical reaction ahead. Hydrogen alone cannot produce ammonia. The second ingredient is nitrogen, separated from the atmosphere using an industrial air separation unit. Although nitrogen makes up most of the air we breathe, it must be isolated at high purity before entering the synthesis process. With hydrogen from water and nitrogen from the air, the plant now has everything required to manufacture ammonia. Hydrogen and nitrogen now converge at the entrance to the Haber-Bosch synthesis loop. Before entering the reactor, both gases are carefully measured, compressed, and balanced to ensure the correct operating conditions. Every system we've followed, from renewable electricity to water treatment, electrolysis, compression, and air separation, has been preparing for this moment. In the next chapter, these two simple gases will be transformed into one of the world's most important industrial products, green ammonia. This is the heart of the entire facility. Hydrogen from the electrolyzers combines with nitrogen from the air separation unit inside the Haber-Bosch synthesis loop. Under high pressure, elevated temperatures, and in the presence of industrial catalysts, the two gases react to form ammonia. The chemistry has been used for more than a century, but the difference here is the hydrogen source. Instead of being produced from natural gas, it comes from renewable electricity, allowing a proven industrial process to produce low-carbon ammonia without changing the chemistry itself. Fresh ammonia leaves the reactor as a hot gas and must be cooled before it can be handled safely. Industrial cooling systems condense the gas into liquid ammonia, dramatically reducing its volume for storage and transportation. Large storage tanks hold the finished product until it is ready for export, acting as the bridge between continuous production inside the plant and the global supply chain waiting outside. The journey that began with renewable electricity now reaches the port. Liquid ammonia is transferred through loading infrastructure and into specialized ammonia carriers designed for international transport. Every shipment represents renewable energy converted into a chemical product that can travel across oceans far more easily than electricity itself. This is what makes ammonia such an important energy carrier. It allows renewable energy to move from regions rich in wind and solar resources to customers around the world. Building a world-scale facility is only part of the challenge. The product also needs long-term customers. Commercial partnerships connect producers with international markets, providing confidence for investors while ensuring reliable supply for future users. Engineering, finance, logistics, and market demand all become part of the same system. Successful industrial projects depend not only on technology, but also on building dependable global supply chains. Before reaching customers, the product must demonstrate that it meets internationally recognized sustainability requirements. Certification provides evidence that renewable electricity was used throughout production, and that the ammonia satisfies the standards expected by global markets. It is the final step that transforms a chemical product into a trusted low-carbon commodity, preparing it for international trade and setting the stage for where this energy will be used next. The story doesn't end in Inner Mongolia. The ammonia produced at Chifeng is intended for customers far beyond China, including markets such as Japan that are actively seeking low-carbon fuels and industrial feedstocks. Instead of exporting electricity, the project exports renewable energy stored inside ammonia molecules. This demonstrates how renewable-rich regions can supply clean energy to countries with limited domestic resources. The real achievement of Chifeng is connecting renewable generation directly to international demand. Wind becomes electricity. Electricity becomes hydrogen. Hydrogen becomes ammonia. Ammonia crosses the ocean and eventually becomes fuel, industrial feedstock, or a source of energy in another country. Every stage is connected, creating a supply chain that stretches from renewable resources in Inner Mongolia to industries operating thousands of kilometers away. What makes this project remarkable isn't a single machine or technology. Wind turbines, solar farms, electrolyzers, compressors, air separation units, and Haber Bosch reactors have all existed for years. The innovation lies in integrating them into one coordinated industrial ecosystem. Renewable generation, digital controls, chemical processing, storage, and global logistics operate as one continuous system. That integrated approach may become the blueprint for future energy-intensive industries around the world. Throughout this documentary, we've followed more than a manufacturing process. We followed renewable electricity as it powered electrolyzers, watched water become hydrogen, combined hydrogen with nitrogen from the air, transformed those gases into ammonia, and followed the finished product onto ships bound for global markets. Every stage depended on the one before it, demonstrating that the true innovation isn't one machine, it's the complete system connecting them all. Projects like Chifeng show how heavy industry can be redesigned around renewable energy without abandoning proven industrial processes. Instead of replacing every technology, engineers are integrating existing technologies into smarter, cleaner, and more connected systems. Whether this model becomes common worldwide remains to be seen, but it has already demonstrated what is technically possible.